Okay, the meeting is now recorded, so let's officially start. Hello, everyone, and welcome to episode 61, already 61 of the Warsaw Quantum Computing Group meetup. My name is Pavel, I'm the organizer, and today we have pleasure to host our great speaker, Adam Wesołowski, who will tell us about graphs, quantum algorithms, and fine-grained complexity. Before we start, um, just a few announcements. So we would like to thank our strategy partner for supporting us, Sonovero R&D, Onyx, Cogit, FinQubit, and Quantum.io, as well as our honorary partners for helping us in advertising the event. And one more thing, if you have any questions, please raise your hand. You can also post your questions on our chat. Adam, would you like to have this meeting interactive so that the participants could unmute and
Yeah,
ask the questions to you?
absolutely. I think it's the best way to have this is just like if you feel like you have a question, you can like just interrupt.
Yeah. So, but just to keep it in an organized way, if you have a question, please raise your hand first, and then we'll try to interrupt. Or
Very,
alternatively, you can just write your question on the chat, and if there is an opportunity, we'll try to ask the question. Okay. So, Adam, if you are ready, the Zoom is yours. So first of all, thanks for accepting our invitation, and yeah, we are
thanks for having me.
started. Mhm.
Yeah, so let me share my screen and let's start. So hopefully this looks well for you. You can see like the first slide should be only the first slide. I don't know
Yes,
how it looks for you.
I
Is
can
it
I
on?
can see it. I can see the first slide only. So actually, beside the or in addition to the first slide, I can also see the tool, right? So there are some options
Oh,
there.
that shouldn't be the case. How do I get rid of this? Can I just enlarge it?
You know, maybe in the at the left top corner, there is maybe an option to present different. I mean, a left corner on your screen. There is yes. So next, left from the name of the file, like WQC PDF. When you go to the left, I can see that there is maybe an option to
You
present
mean
another view. To the right from here.
to the right, you mean? Okay.
Um,
So screen sharing, annotate, remote show meeting.
I'm not
Okay,
sure
no,
if I
not
see
that.
exactly
Okay.
this. Yes. But anyway, it's not a problem, Adam, for us. So
Yeah, okay. So like, but if you can see it clearly, then I think it's
yes,
should be
yeah, at
fine.
least at least I can see your slides clearly.
Yeah, like shouldn't be bad. Okay. So yeah, welcome everyone. So my name is Adam, and today we'll have this little talk about graphs, quantum algorithms, and lower bounds. And I don't know your background, so I presume this title may be scary for some of you. For some of you, it may sound, like quite easy, depending on what your expertise is. But my plan for this talk is not to get into too much technical detail. In fact, it will be predominantly like just an overview of the field. I'll talk about interesting things like interesting stories and basically what can you do like with graphs and quantum algorithms.
Actually,
So hopefully you'll get something out of this. And yeah, like hopefully it will be interesting to you. So let's start. So, a little plan for today is basically three topics that we'll go quickly through. Is tools for quantum algorithms. So, what tools can we use that can help us in quantum algorithm design for graph problems? Then this will be like very basic, quite old techniques, um, but we'll just mention them. Okay, then we'll mention a couple of graph problems which are not, like very difficult, but they are from the complexity class P, but still, present an opportunity for quantum algorithms to show some advantage over classical algorithms. Okay, and we'll conclude with a short discussion of lower bounds, quantum lower bounds, and this will be, I think, the most advanced part of this talk. And not that it will be very difficult, but conceptually, I think this might be the most difficult part. but also the most interesting part. So let's get to it. Okay, so just before we start, I would like to set the ground for uh, the notation, basically, like for what we'll be referring to, like some words and basically the framework we'll be operating in. So um, in quantum algorithmic research, we very often consider what's called query complexity of the algorithm, which is not exactly the time complexity. It's very often like very similar, like differing by a log factor or something, but it is different conceptually. So if you imagine that you have this oracle, which is, like you can think of it as a device, as a specific algorithm. We do not count how many operations this algorithm performs. We count how many queries to the input it makes. Uh, and that is sort of easier because, the algorithms can do crazy, complex things. And, it's sometimes hard to count it. Whereas it seems very fundamental just to ask the question, how many queries to the input does your algorithm require to solve the problem? It seems like a much simpler framework, and indeed it is, and it gives very good results too. So that's what we'll be talking about. In terms of complexity, we'll be referring to query complexity. Um, okay, so query complexity, like the input can be given for graph problems, it's usually given as an adjacency matrix of the graph or adjacency list of the graph. So uh, right, adjacency matrix is just a matrix, and it has entries which correspond, like it's an n by n matrix corresponding to the vertices in the graph, and there's the input in the matrix is one if there is an edge between the corresponding nodes, like ij, right? And if there are no nodes connecting two vertices, then the input is zero. Okay, and then there's adjacency list, which is like you have a list of nodes, and next to each node you have basically a list of its neighbors. Okay, so these are just two models which are in a sense equivalent in terms of like how hard it is to operate on these, but they provide advantages depending on the type of your graph. But essentially you shouldn't worry about like what it is. It is just like a different input type, different ways of encoding the input. Okay, so moving forward, uh, we'll talk about like some tools that, like these are very standard algorithms that quantumly you can do better. So if you want the unstructured search for a good element in a list, then you know that quantumly you can do that in a square root of n time, whereas classically you need to explore the whole list. Like so you need to make like n steps, right? And quantumly it has been shown that via Grover search you can basically get this quadratic speedup. So it is less known, but it's still very, very popular result. If you have k good elements in your list, so the square root of n is like the worst case scenario, right? Where you have a list of n elements and only one of these elements is known to be like the good element. And then it's square root of n. But if you have k good elements, then it's square root of n divided by k. Just to, like so it's fun fact, basically. And then unstructured search for k good elements. So if you want to output k elements, not one element, sorry. So if you want to output k good elements of the list, not just find one of them, if you want to output k of them, you need, that's not correct. That should be under the square root. I'm sorry. Yes, that should be, yes, it's here, it's correct. A typo, I guess, during the presentation. So you need square root of k times n queries to your list to output k good elements. Okay, and then minimum finding. So minimum finding, like similarly, if you want to output k minima, of your function, like then you also need by the same token basically via Grover search, you need this number of steps, and all of these provide a quantum speedup over their classical counterparts. So classically, you cannot do these tasks so fast. But for example, the sorting a list is an example of a problem for which there is no quantum speedup, because it has been shown that the optimal algorithm is takes n times log n steps, which is as good as classical algorithms. So sorting, you cannot sort your list faster quantumly. That's just a fun fact again. Okay, so let's move to the list of problems that we will go through today. So we'll talk about all of these and quantum results for these problems. And we'll also have a little side note, which will be a very interesting story on a particular quantum algorithm, which was super counterintuitive for many people for a long time. But yeah, let's start with ST connectivity. So ST connectivity is a problem where you're given an, say, undirected graph, and you ask whether two vertices in that graph are connected. So it seems like a very simple problem. And classically, in the worst case, you need to explore all the nodes in the graph at least to show that these two are connected. But quantumly, you also you'd like to show that there is a path between these two vertices. Basically, if you can find the path between two vertices, then it's like a witness to the connectivity, and then the algorithm can accept. Okay, so this is the problem. So given a graph and two vertices, the problem is there a path, or are these two vertices connected in the graph, right? And quantumly, it has been shown that the optimal complexity, you need n steps. You need n queries to the adjacency array, and you need n to the 3/2 queries to the adjacency matrix. So in other words, you need to learn the whole graph, because in the adjacency array, making n queries to the adjacency array is essentially learning the graph. Similarly, the adjacency matrix. So these are the results from 2006. So these are not, it has come a couple of years after the Grover search algorithm, etc. So it hasn't been an instant result. And so this is the paper which provides a lot of complexity results. And I can highly recommend for anyone who's interested in the field. It's a good source of knowledge. Okay. So that's the ST connectivity. So that was just a little mention. We will go through these problems like that with very short slides, and then we'll go into more interesting, more in-depth stories about certain specific quantum algorithms. Okay, so APSP problem, meaning all pairs shortest path problem, asks for all pairs shortest paths in an input graph. Okay, and this is very interesting because this story is already classically, you can imagine that this problem is as popular as they come, and it has been very well explored. A lot of research is on this problem, and it is believed that no faster algorithm than the cubic time for dense graphs, so the worst case scenario, exists. I included this O of n to the 2 omega, which is the complexity of matrix multiplication, because there are these matrix multiplication algorithms for solving this, but this is a different story. So we'll disregard them, that they are not, depending on how you formulate your problem. In general, it is believed that no faster algorithm than n cubed exists for outputting all pairs shortest path. And no subquadratic algorithm exists for APSP on sparse graphs. So on sparse graphs where the number of edges is order of number of vertices, you cannot solve it faster than n squared. So truly, like, on sparse graphs, you need these n squared steps, where I should mention at the beginning, because for people who do not know the convention, n is the number of vertices in a graph, and whenever you see m, lowercase m, that will be the number of edges in the graph. So, okay, so this is a very, very big result. So that no subquadratic algorithm for APSP can exist unless Seth fails. And what is Seth? That's strong exponential time hypothesis. And well, that is something that, that hypothesis is believed to be true. Like it's a very, very strong thing, but it's also, we'll comment on that when talking about lower bounds. Because this is, a lower bound technique, basically, where you show that conditioned on some hypothesis being true, you can show lower bounds. So if this hypothesis fails, then you may get some better algorithms, but if this hypothesis is true, then you cannot. Okay, but that's a story for later. So that's the classical complexity of solving the APSP. Now, wrong. Okay, so quantumly, it has been very recently, I think like 10 years ago, okay, so not that long ago, it has been shown that you can solve APSP faster. And this paper incorporates basically a Grover search, but it's not straightforward to apply it. But this quadratic speedup that you can see is in the dense case is essentially, again, they're like believed to be optimal. So in the quantum case, is again not believed, like the APSP is not believed to be solvable faster than n to the 2.5. So there is a speed up, but it's again like it's very hard to find faster algorithms, and it's not believed to be true that you can find faster algorithms. Okay, so this is the APSP problem. Now we'll move to the SSSP problem, which is the single source shortest paths. So that's a different setup. So you are given a graph and you are not asking for all pairs shortest paths, but you want shortest paths only from one vertex. So you want to learn like all shortest paths to all the other vertices in that graph. Okay, and that problem, intuitively should be easier, and indeed it is easier. So classically you solve it via the Dijkstra algorithm. It's like the I think like the one of the most popular algorithms, which requires order of m steps. And yes, and here quantumly it has been shown also like in the same paper, which I mentioned already, that this quantum Dijkstra so-called is solvable in square root of nm steps, which you can convince yourself is a little bit better than order of m for some cases, for some more dense cases than so this is slightly better than classically. And yeah, this is again this reference to this very good paper. And yeah, and this is believed to be optimal. So the claim is that you cannot really solve SSSP faster than square root nm. Okay, so SSSP, so we went through this. So, oh yeah, so now it's a time for this short story about a crazy quantum algorithm. So it was in 2013 that Alexander Belov showed that there exists a specific, quite complex quantum algorithm that decides the ST connectivity without giving you a path. Because, okay, classically, usually you'd employ some, path finding algorithm on your graph, like, breadth first search or depth first search or Dijkstra, in search, for a path from one vertex to another. And if then this algorithm, if you decide the connectivity and you decide that two nodes are connected, then usually as a byproduct of your algorithm, you can also output the path between the two vertices. And this is really intuitive. Like, how can you say, like, how can an algorithm decide connectivity without finding a path? So in 2003, Bell showed that there exists such a quantum algorithm that decides ST connectivity, and it doesn't give a path. So it may output, yes, for example, that S and T are connected in the graph, but you cannot extract a path from the output of the algorithm. So and that was really counterintuitive to many people. And well, this work of ST connectivity. So I'm recalling this graphics from earlier, just to show you that, yeah, like just to remember what the problem statement is. Um, that this algorithm has complexity of square root of Lm, and it decides basically connectivity on that graph. And L, the lowercase l, in this case, is the length of the path. It's an unknown a priori, but it's the length of the path, shortest path between S and T in that graph. And you can iteratively guess this length, and there's an additional log factor, but we don't care about this. And the algorithm that decides ST connectivity in this many queries. So ever since that work, it has been an open question whether there is some algorithm that can find some information about the path, right? So that it can decide the ST connectivity maybe, and output something else. Like we would like to learn something about the path in similar complexity. And it was like for a long time, people like couldn't find anything. Like there was no indication that you can find any information about the ST path in similar complexity. And yes, right. So there's been this open question, and only last year, Stacy Jeffrey showed in this paper with her colleagues that in the detection, the path detection complexity, because like this connectivity, you can think of it as a path detection, right? Because if we decide that S and T are connected, then we detected a path between S and T in that graph. So we call it a path detection algorithm. And yes, they showed that they can find an edge on that path that connects S and T, but they cannot do much more in the same complexity. And yeah, and only this year, like that's been like one of my works, that one of my projects I've been working on. As you can see, we showed that in some instances you can find the entire ST path in the detection complexity, and moreover the shortest ST path. So we really showed that like in some instances you can extract there's an algorithm which solves the ST connectivity, but also gives the entire path, which has been, an open problem for, more than 10 years at that point. But yeah, this paper by Stacy Jeffrey was a big breakthrough, and we basically used a lot of ideas from their paper to improve upon. um, yes, so this is like a short story about this crazy quantum algorithm, because as you saw, like for 10 years, there have been literally no works showing any progress whatsoever on whether you can extract some more information about the path in this very low complexity. Okay, so going back, so really like based on, I'll go back for a second. So as you can see here, the claim is that we can find the entire shortest path between S and T in some very low complexity, right? Which is the detection complexity, which is again like this square root of Lm. And this opened like if you look at it from another perspective, like classically, you cannot find a path, a shortest path between two vertices in your graph without, finding essentially all other shortest paths. So classically, the Dijkstra algorithm, which uses, order of m steps, is basically solves you the single source shortest path algorithm. Whereas, quantumly, we showed as a byproduct of this result that you can find single pair shortest path faster than via SSSP algorithm, because quantumly you could also apply quantum Dijkstra, algorithm, which would, be square root of n times m. And, you could also solve your single pair shortest path. But this square root of L times M is slightly faster, like especially like when L is, like constant or like polylog. Uh, but like in the worst case, right, like the L, the length of the shortest path between S and T might be N, might be order of the number of vertices, and then like we are no better than quantum Dijkstra, but on some other instances, we are. So this is like, like like an algorithm with complexity parameterized by the length of the path, which on its own is also like a nice result. Um, yeah, well, yet from another perspective, just to I actually won't go into this because there is a space complexity problem, because now what we are talking is all like the query complexity, like like how many queries, like how many steps do we need. But with every quantum algorithm, there's also this discussion about how much memory or like workspace does it need to execute the algorithm. And yeah, I will not go into this because we don't have time, but I highly recommend to, if you are interested in that, it's a great, great area of research. Anyway, so I think it's time to go into lower bounds. So just before we start, just some informal definition of what a quantum query lower bound is. Um, so it is simply, like the minimum number of times your algorithm needs to access the input of the problem to be able to basically decide the given problem. And yeah, and this is very fundamental. Like if you think about this, you are showing this. This is like regardless of any implementations, regardless of any algorithms, regardless of how good algorithm you can come up with. Like you are showing really like inherently how difficult is the problem. Like such that any algorithm that exists, it certainly needs to use at least this many steps. So you are showing like a very fundamental thing when you prove a quantum query lower bound. So uh, interestingly, like I believe so that this is finding quantum query lower bounds is one of the, if not the most difficult uh, area in quantum algorithmic research, because it's super difficult to show like non-trivial lower bounds. Okay, um, so let's get to it. So I'll mention three techniques that can be used to search for quantum lower bounds. And first, the first technique is a reduction from a problem with a known lower bound. So what does that mean? That means that um, you show that if there's a graph on which, so let's take a specific problem. So let's say we want to prove the lower bound, quantum lower bound for connectivity. Okay, so we take some graph and we say that if on that graph we could solve ST connectivity, say faster than linearly, then this would imply that on some other graph we can solve, for example, traveling salesman problem in polynomial time. And that would be, like a reduction. And if it is believed, or there is a known lower bound that TSP cannot be solved faster than, by like in exponential time, then this means that this is like a contradiction, which implies that, this is a lower bound, that you cannot do it faster than linearly. So I don't know if it's clear. Let me restate. So you have a problem, you take some problem with a known lower bound. So suppose you know that search, for example, like search of an unstructured search cannot be done faster quantumly than square root of n, which has been proven. So Grover is optimal. Like square root of n is as good as you can get. So this problem has a known lower bound. And now you say that you can construct a graph such that it would like like an algorithm for ST connectivity that runs faster in than order of n would imply a faster algorithm for Grover search. And therefore you get a contradiction because you could do Grover search faster then. But these reductions are very difficult to find. As you can imagine, like, like I don't know, there's no reduction from ST connectivity, like from Grover to ST connectivity, but that was just an example, right? But these reductions are generally very, very, very difficult to find. But again, this is the most um, accessible technique. This is like very, very often like people just resort to finding reductions, which is difficult, but is the most accessible technique. So the other technique is the so-called adversary method, and this is recently new, but like not very new at this point. Is the adversary method developed by Ambainis, and this adversary method is basically like a tool for showing quantum lower bounds, and the other technique is the so-called polynomial method. And as you can see, these are more than 20 years old, but they are still very good techniques, and they are very much in use currently in research. So the adversary method in particular, or the so-called generalized adversary method, is known to give optimal lower bound. So if you prove a lower bound with the adversary method, it is known to give optimal results. So such that, it gives the accurate lower bounds such that, like no better lower bound exists. Okay, so in this talk, I think I will focus only on the first technique, and we'll try to perhaps give you some examples. Um, so in terms of like, like the reduction, because I don't think we have time to go into adversary method theory, but I definitely recommend that. It's a very powerful technique. I think one of the adversary method is the most powerful technique for proving quantum lower bounds. Okay, so we'll now move to the other problems that I mentioned for graphs. So vertex eccentricity, that's a very standard thing. So the vertex eccentricity of a vertex V is the maximal maximal length of across all shortest paths from the vertex V. So you compute, like all shortest paths from a vertex, then you get their lengths, and the longest is the eccentricity of that vertex. Okay, so quantumly you solve that via the SSSP problem, with some post-processing. So you just solve all shortest paths from the vertex, and you then just find the path with maximal length, and you output the result. But the best known lower bound for this problem is omega n, right? And it doesn't seem like this is optimal. Like it doesn't seem like there is an algorithm in the dense case, at least, where you could just traverse all vertices and solve the eccentricity problem, because there is this additional structure that you ask for the shortest paths for the from the vertex, and it seems like this lower bound is not very good. Like you would believe that the square root nm algorithm is correct. So yeah, it has been only recently. Oh, there is a square root missing. I'm sorry. There should be a square root over n times m. So yeah, it has been recently improved to show that this algorithm, that solving eccentricity via quantum Dijkstra, is essentially optimal up to some polylog gap, which still exists. Okay, so diameter now is, what is diameter? So the diameter is the maximal eccentricity for any vertex in the graph. So it's like the longest, shortest path that exists in your graph. And okay, so yeah, sorry, I restate the definition. So with radius is the minimum eccentricity for all vertices in the graph. And interestingly, this is a very big result. It has been shown that radius on dense graphs is as hard as all pairs shortest paths. So is it obvious that it is true. So normally you'd think like, how can you solve radius or diameter? So you can solve all pairs shortest paths, and then like you have as your output of the algorithm, you have all shortest paths, and you can just search for the path with minimal length or maximal length, and then output diameter or radius. Okay, but there are smarter ways to go about it. Like you could think that there are smarter ways to go about this, and the answer is that on dense graphs it is impossible. So radius is as hard as a PSP problem, which is a very non-trivial proof, and it's very recent result. But then diameter equivalence has not been shown. So diameter can be easier than a PSP problem. Because if you think about this is a very big open question in classical algorithmic research too, whether you can solve radius or diameter faster than via all pairs shortest path. Because diameter and radius only ask you for just one number, right? They ask you for the length of the longest or the shortest, or no, like for the diameter, it asks you for the longest eccentricity, and for radius, it just asks you for the shortest eccentricity in the graph. And APSP algorithm outputs like the witnesses, like outputs all paths, all shortest paths in the graph, which seems redundant just to output like a single number. But people like, cannot show like that there's any discrepancy that you can do diameter faster. Okay, so it has been actually shown that, for sparse graphs where APSP takes n squared time, diameter cannot be solved faster than n squared. And the reduction from CNF-SAT, so CNF-SAT is the so-called conjunctive normal form satisfiability problem, which, under the strong exponential time hypothesis cannot be solved faster than via exhaustive search, which takes exponential time. So this reduction is, again, it's a very non-trivial result. So like, I don't expect you to have an intuition on how this reduction looks like. But the result stands that the point is that diameter cannot be solved faster than n squared time. And similarly for radius, it has been also shown that via heating set conjecture. So heating set is a problem where you have sets, and like the heating set is a set that has a non-zero overlap with every set that you're given as an input. And yeah, it's just yet another problem which is believed not to be solvable faster than some complexity. And under this, you can show the hardness of radius. Okay, so yes, so as I mentioned, the very big open question in the field is whether you can solve, in particular, diameter faster than via all pairs shortest paths. And if you have some good results on it, you can certainly get very famous on this. So in the quantum setting, going back to quantum algorithms, all pairs shortest paths, as I mentioned, admits this slight speed up, so it can be solved in n to the 2.5 queries. So like quantumly, it follows that you can solve the diameter also, like in the same time, right? In the same number of queries. So this is obvious. But also, interestingly, something that doesn't happen classically, diameter and radius also, they both admit this very efficient algorithm, which runs in n times square root of m, and it's way faster, like in both sparse cases, so both m equals n and both m equals n squared. In both cases, it admits like faster algorithm than APSP. So there is indeed quantumly this separation that diameter and radius are easier than an APSP. And this is like a really important result because it shows you that classically there is a proof of APSP to radius equivalence, meaning that if you can solve one faster than than n to the third power, then you can solve the other faster. But quantumly, you can solve radius way faster than you can solve APSP. And this breaks down the classical complexity relationships, where you show that problems, are of equivalent hardness, or, faster algorithms for one imply faster algorithms for the other. Quantumly, it doesn't hold. So this is a very important note to realize that it is not the case that if two problems are equivalently hard classically, they are equivalently hard in a quantum setting. So yeah, this is really important, and this is really, really important regardless of the comparison to the classical complexity landscape. It is important result on its own because it is the fastest algorithm for diameter computation. It is faster than the APSP, obviously, as we mentioned, but it is also faster than the matrix multiplication algorithms, which for dense graphs are basically state-of-the-art algorithms that have the best complexity. So, for n equals m equals n squared, this is just the quantum algorithm is quadratic time, whereas the best classical algorithm would take, n to the 2.37, whatever the currently best matrix multiplication exponent is. Yeah, the quantum algorithms are here showing huge advantage, and they break down a lot of classical intuitions that you may have. So yeah, moving further. So you would like to know what the lower bound is, what is the minimum number of steps that you need quantumly to solve the diameter problem, because so far there are no lower bounds, no lower bounds for diameter, that would tell you that you can expect some minimum. So currently, because of this algorithm, this quantum algorithm that works in n square root of m, people started wondering how far can it go? Are there any better algorithms than the n square root of m? And well, the best lower bound that you can get for diameter is omega n currently, right? So I've been trying to actually look at this problem, and together with my supervisor and some of our friends, we've been trying different reductions. So we tried, reductions from parity, which wasn't a very smart move. But then we tried a reduction from the problem of collecting triangles. It's also a very well-known problem in algorithmic research. And this was already a smarter move, but it gave us the same linear bound for diameter. So we are not very happy. With the linear bound is sort of like the intuitive bound that you would expect, that it would be very weird if you could solve diameter faster than, for example, connectivity, which has this omega n lower bound. And we tried very advanced techniques. So we tried, the quantized classical reduction for diameter, which I mentioned from CNF SAT. We tried this under the quantum strong exponential time hypothesis, which is the quantum version of the classical one. But although they were promising, we were expecting to get a better lower bound. They all gave this expected obvious omega n bound. And yeah, and the big question is, can you get a better bound? I mean, ideally, you would like to get the bound that is equal to n square root of m, because that would mean that this algorithm is optimal, that you cannot do any better. This algorithm is as good as they come. And so you cannot hope for any better. So we are looking to improve the lower bound. And the potential candidate would be the complexity of minima finding, which I mentioned at the very, very beginning. So minima finding, if you have a function and you want to find k different minima of that function, and these minima can be of different type, whatever that means, right? Like so like different parts, different intervals of the function, right? Like can be the type of the minimum, and you want to find k different minima of your function, and there's an established lower bound for this, which tells you that if you're looking for d minima and you have like like a discrete function with like n values, then you need like necessarily you need square root of d times n steps. And yeah, and we were able actually to show that all of these problems admit this new lower bound. So currently, like it doesn't help for the sparse graphs where m equals n, because you can see that you again recover this omega n lower bound, which is not very helpful. But it tells you something more, right? Because on dense graphs you are already at n to the 1.5. So in particular, this allows us to almost close the gap up to this log factor, right? So which is very often just discarded, but technically we haven't closed the gap, but we came very close. But it essentially means that probably the SSSP algorithm is optimal for eccentricity finding. And interestingly, like you can see that there is this quadratic gap between the upper bound for radius and diameter and the lower bounds. So currently, like it is, I think, one of the big open problems uh, to find some better lower bound for these problems. So if you happen to work on like lower bounds classically or quantumly, then I invite you to look into this, because it seems like a very difficult problem. Um, and yes, okay, so do I have anything more? Yes, so just takeaways from the today's talk. So I hope it wasn't too fast. I realized that it might have seemed a little bit unstructured, but that was really the plan for the talk, just to throw some results at you, to basically share some papers with you, which I deem to be, um, interesting, and they contain interesting results, which if you work on quantum algorithms may help you in your work. And so the key takeaways, like if you just happen to register for this talk out of generic interest in quantum algorithms, the key takeaways are that quantum algorithms might yield very counterintuitive results. And I refer to the path detection algorithm, especially here, where you can solve ST connectivity without finding a path between two vertices. So you can truly like correctly decide the problem, which the more you think about this is the less intuitive it is, right? So the other takeaway that I would like you to remember is that classical hardness relations may not hold in the quantum regime. And here I'm referring to the radius APSP equivalence, which holds classically, but is very far from the truth in a quantum setting. So yeah, and then the third last takeaway is that proving quantum lower bounds is very, very hard, but it's very, very rewarding, as it shows you the fundamental, like inherent problem, uh, inherent hardness of the problem, which is like something of a philosophical nature. Yeah, and we deem to be like very important in algorithmic research. So these are the three main takeaways. I hope that yes, that my talking wasn't too fast or too slow, that the slides were not very overwhelming. Possibly they were underwhelming a little bit at many points, but yes, I hope that you have something of value from this talk. And yeah, thank you for joining. And yeah, and thank you, Pavel, again, like for inviting me to give this talk. It's been a pleasure. And if you happen to have any question, then I am happy to take them now. So
Yes, thank you. Thank you very much, Adam. That was a very nice presentation, and do not worry. I think that the slides were very good. So we just received a question. Can we get the PDF? So if you want
oh,
to share
that's
the PDF,
that's
you
a
can
very
do.
nice question. I appreciate that.
Yes. So if you can, you can later share with me the PDF, and I can also upload it
Absolutely.
to our website.
Absolutely.
Actually, we've also received another question. So there
Yes.
was a question from Mohammad Reza. It was already asked um, closer to the beginning.
Oh,
I
yeah,
missed.
now I can see. Yes.
Yes, you can say it for ST connectivity. What was meant by theta n and theta n to the
Oh,
power of 3 over
very good question. So that's something I probably should have included as part of the presentation. So there are these different notation conventions. So you use O for the best algorithm. Like if you have an algorithm that runs in some time O, the like n, sorry, like times n squared, then denote that as O(n) squared. And if your algorithm is optimal, meaning that there's a lower bound of omega n and a corresponding algorithm that also runs in this omega, like in this n complexity, then you denote that as theta n. So the theta basically means that the algorithm is optimal, like that there is a corresponding lower and upper bound uh, to this n complexity. Um, so yeah, and omega obviously refers to the lower bounds, right? So like the worst case hardness. Uh, is that the answer? Like, is that what the question asked, or have I misunderstood?
Let's see, because I see that Mohammad Reza has asked another question. So
Frequencies are supposed to compute.
let's read it. Under what conditions would changing a problem statement slightly change the quantum lower bound drastically? Is this somewhat chaotic?
Um,
It can happen actually, Mohammad Reza. At least in classical computing, it can happen that adding some, let's say, slight
oh,
modifications to the problem can lead to totally different complexity,
yes.
But
computational complexity.
In a
so,
quantum
but
setting,
is this the case for the quantum uh, case? Yeah. Is it similar in the quantum case?
so
Uh,
like certainly there are problems, which if you modify it very slightly, become suddenly way more difficult. But if you are referring to this ST connectivity case, right? So you're asking about this particular example, or like is it a general
yeah, in
question?
general, yeah, in general, yeah.
Okay, in general, yes, like this happens. So if I wanted to give you a best example, uh, what would be the best example for that?
Mhm.
Mm, that no, that's a fair question. Like out of my head, like I cannot
So,
like
Adam, I have a good
good
I have a
problem.
good example related to sorting. So in general, when you want to sort an, let's say, arbitrary set or list of elements classically, then the, let's say, the lower bound complexity is n log n, where n is the number of elements. But when you ensure that your elements are from a relatively small range of values, then you can do something that is called a bucket sort, and then you can do it linearly. So this is one example, right? So adding some constraints on the possible values of the elements that you sort may already
Oh.
change the complexity of the problem. And I know that there are many similar examples, even in the graph theory. You know, for example, the traveling salesman problem on an arbitrary graph is NP hard, but when you
Yeah.
add some, there can exist some specific constraints for the graphs that may that may just reduce the
The
complexity of the
complexity may
problem
put the problem in.
and make the problem solvable in polynomial time. And
Yeah, exactly.
actually,
So
yes,
that's what I was thinking about. Like,
yeah,
because
yeah,
when you ask like a drastic change, I was thinking like exponential to polynomial change or the other way
yeah.
around.
Yeah, yeah. Even in that nature, I was actually, yeah, alluding to that.
Mhm.
Yes. So
Another case is
Change it there.
factorization. Actually, if you want to factorize arbitrary numbers, then so currently we do not know the polynomial time classical algorithm. We know
Yes,
the polynomial time quantum algorithm for this, but it hasn't been proven that the polynomial time classical
yes,
algorithm does not exist. But actually,
right.
when you restrict the set of numbers that you consider, and you do not consider all possible numbers, but just some specific numbers, then these problems can be easy. So this is one of the reasons why it's very important to set the keys for your encryption algorithms correctly. So
Yeah.
they cannot be
I
any
just,
arbitrary numbers.
yeah. For my last question, so there was a claim that there was no quantum improvement for sorting of the
Mhm.
classical case, right?
Yeah, yeah, right.
So is this proven or?
Yes. So I can refer you actually, I can send you a
Yeah,
link
yeah.
to a paper which proves that there's no quantum speed up for some.
That's interesting. Yeah, yeah. That would be nice.
Just give me a second and I'll send you a link to the paper, which proves the quantum lower bound is n log n uh, for that problem.
And are there other cases in which there are no improvements? And I mean,
So okay, so here it
proved.
is. Just
Yeah.
the link is in the chat. And other problems, yes, yes. So there are a couple of examples
Hmm.
where, well, but like this is different because there are examples where it hasn't been shown that there is a speed up, but it hasn't been
No.
proven that there isn't one,
Yeah,
right?
yeah. That's my question. Yeah.
So
Proved.
okay, about the proof. So I no, I think there might be some additional, but I'm not like I cannot
Oh,
give them
okay.
now.
All right. All
I
right.
presume there are a couple of other problems with proven runtime that is equal to the classical.
Okay.
Mhm. All right.
But
Good.
sorting is a very popular example. Like sorting is one of the like flagship examples where you cannot that there's no quantum speed up and it has been proven. So this is in the paper.
Yeah.
So,
This is interesting because in general it's very difficult to prove
yeah.
that there
Mm,
is no quantum algorithm that can give an
Yes,
yeah.
advantage.
Yeah. This
yes,
is special. And are there cases for which there's a proof that the classical case is better overall under any circumstances over the quantum case? Proof, mathematical proof.
I don't think this can be the case because
Uh-huh.
anything that you can
Uh-huh.
do
Yes.
classically, you can do quantumly,
Mm-hmm.
but the opposite is not true, right? Like not
Mm-hmm.
everything
Mm-hmm.
that is doable quantumly in some time is doable classically, but like
It's,
quantum is just like an extension of classical.
yes.
But
Because it's the possibility. Yeah, it makes sense. Yeah. Improves the possibilities. Yes. So
All right.
thank you for.
We have one more question from Aparajita. How do quantum lower bounds for path detection and shortest path problems challenge classical algorithmic assumptions?
so classically, to find a shortest path between two vertices, uh, not even intuitively, uh, you need to explore the whole graph. Like you need to explore all edges, like so order of m. Because like intuitively, like you can think that, okay, imagine like you explored almost all edges, like but not all of them. Like how can you be sure, how can you classically guarantee that the path that you have found from one vertex to another is indeed the shortest path? Right? And I'm not talking about special cases, I'm talking like the general problem instance. And in general instance, you cannot be sure. Classically, if you haven't explored all edges, then you cannot be sure that you have found the shortest path from one vertex to another. So classically, it is the number of edges m that provides this bound, and it is not, I think, even like reasonable to expect classically to for it to be doable faster than m. And and in particular, classically, there is no distinction between single pair shortest path and single source shortest paths because of yeah what I just said, that you need to be certain that you found the shortest path. And so how do quantum lower bounds for detection challenge? Yeah. So are there like
We've already discussed it. So that's the
yeah,
question that we've already discussed.
okay,
That's the
yeah. So
question.
yeah, sorry. So that yeah, that's
Yeah.
the same thing. Okay.
Okay.
Yeah, I hope that answers. Like, if do you feel like I answered your question, or were you having something else in mind? Yeah. Okay.
Yes,
Very,
yes,
very,
for
very
sure. Okay, good. All right. Okay. Do we have more questions to Adam? If not, then Adam, thanks once again, and
Thank you very much.
we'll contact you later regarding the slides and of course regarding the recording. And yeah, let me maybe share my slides once again for a while, and I just would like to announce our next event. Uh, so I'm not sure if Krzysztof is with us, our next speaker, but if not, then that's not a problem. Okay. All right. I hope you can see my slides now. All right. Good. Uh, yeah. So we thank you for your attention, and if you are interested in our activities, other events that we organize, let's stay in touch. Feel free to join our mailing list, our social media groups, follow our profiles, our YouTube channels, subscribe to our newsletter. So we thank once again our strategic partners for supporting us. Novera R&D, Onyx, Quantum.io, Cogit, ThinkQubit, and we thank our honorary partners as well. If you like our activities, you can also donate. So there is also an option to donate 1.5% of your tax if you pay your taxes here in Poland. And we'd also like to invite you to our next Warsaw Quantum Computing Group meetup, number 62 already. Krzysztof Pomorski will give a talk about the strategy of integrated classical quantum chips development in Poland. So it will be exactly in 3 weeks from now. Okay, that's all from my side. Here you can also see some useful links follow, and yeah, thank you everyone once again. Thanks for coming. Thanks for all questions, discussions. Adam, thanks once again for the great
Thank you very
presentation.
much, and thank you for these great questions. Yeah, and hopefully see you in the future
Yes.
at some point.
Yes, we hope to see you next time. Thanks, guys. Bye bye.